Looks like I'm live. Good evening. Formality, blah, blah. So, I have a topic today. Previously, we talked about time interrupts and some live lessons. So tonight, we're talk about ADC. For ADC team, it should be a refresher, I guess, for you guys. I hope. So, like usual, I like to ask, why do we have analog to digital conversion in our CPU, in our controller, in our computer? Why do you need this question mark?
The way computer interfaces with the physical world.
Yeah. Can you elaborate? Why do you need this conversion to go from the physical world to the digital world?
Quicker to compute?
Not only quicker, it allows you to compute, right?
The ones and zeros.
Ones and zeros. Yeah. From what?
From hot, cold, push, pull, heavy, light.
All over the place.
Yeah.
So you have all kinds of energy forms, right? You need to convert it to something that the computer can measure. So first you have to convert it to electrical energy. So how do you describe the electrical form of energy?
Voltage.
One of the parameters is voltage, right? Voltage or current. And what are the characteristics of these measures?
Amplitude.
What have you noticed about digital computers? The way it describes things, as opposed to the real world or the physical world. Not saying computers not physical, but
Quantify it.
Quantify or
Steps. It's
discrete. That's the term, right? Things are treated discretely, as opposed to what in physical world? Sinusoid. How does it look like? Smooth, right? What's the proper term for a function that is not discrete? Calculus. Invoke your calculus. Indiscrete. Shameless, huh? The physical world is shameless.
Dynamic.
exponential.
Not dynamic. Dynamic is different. Well, it is like exponential has this characteristics. Exponential function has this characteristics. You have discrete and you have continuous. To review your math classes, guys. So that's so the physical measures are continuous. So when it goes to digital, it must become discrete, right? Because if you have a continuous things, how many bits do you need to represent something continuously? Infinite, right? Do we have infinite bits? No, that's why we have discrete values. So we want to get these physical characteristics into a digital values, represented as digital values or a combination of bits. This is what we've been talking about since week 1, right? Getting everything into a combination of bits so you can actually do computation. Because when it's just a digital value, you can put in a register and you can do all sorts of stuff. Arithmetic, modeling, whatever, with the computer. Why? Why computer? Why can't you just do it on paper? Because it's cool, I agree. It's much faster than we are. There were analog computers, right? So before transistors make digital computers very easy to use and manufacture, relatively speaking, we had analog computers to do all kinds of arithmetic. So how do we get to how do we convert all these analog values? In our case, voltage or current, usually voltage. But if it's current, can you convert to voltage?
Yeah.
Yeah, right. When we get it to as a digital value, that's even more recent than your math classes.
Oh, V equals IR is the only really one I remember, so.
That's all you need, man. Until you get to your
T equals VI.
non-ohmic devices. Oh man. So it's usually implemented with a comparator and a DAC, which is a digital to analog converter, which is easier to make. Did you do that in your circuits class? Making a DAC?
Comparator out of an op amp.
No, DAC. You can look up Wikipedia for that.
Does it have something to do with 4 diodes?
Whatever.
Yeah.
It's not-
Sure. So the first thing, when you convert, like I said before, when you convert to analog to digital, something continuous becomes discrete. Right? When you do this, some information is lost. There's no way around it. This is what we mean by the precision of the measurement, right? So the smallest unit of measurement of something. So analog signals are continuous, but the representation of an analog signal as a digital value is discrete. For example, let's say we have a 2-bit precision for our conversion. So we have 4 distinct values, right? So if we want to convert a voltage that goes from 0 to 3 volts, and you only have 4 values, then you can only have 4 intervals between these two, in this range. That make sense? So let's say we have 0.9 volts. What would you get in your register when you do the conversion?
1, 0, 0.
No, 0.9,
Oh, wait, that's 0.
0, 1, right? Well, about 2.6 volts,
1,
1, 0.
2.6.
Yeah, 1, oh, 1, 1, sorry. 1, 1, 1, 3.
Use it.
Exactly, right? So you lose information. Like 2.48, for example, it will still be a 1, 1. So this may be sufficient for your application. Will this be sufficient for something like temperature? Probably not. But depending on your actual range, it could mean freezing, all right, hot, oh, super hot. Or it could mean nothing, it's the same, right? Because you don't have enough precision. So this thing, when you have a continuous value and then you have a discrete value trying to approximate it, it's called, and the loss of precision is aliasing. Right? So the resolution will be the number of bits, and if you raise 2 to the number of bits, you'll get the total number of intervals you can have in your conversion. So the greater the resolution, the greater the precision. So the precision will be just the high reference minus low reference over the intervals. Right? In this case, your precision will be 0.75 volts. So what happens when you increase your precision? Or you increase your resolution?
More steps.
Lose range
Do you lose range?
if you with a given number of bits.
Let's go to 3 bits. Does it approximate the function better, the voltage better? Yeah, you actually can look at a more precise value in the expense of having more bits. And in some implementations of ENSC, when you increase the number of bits, it takes longer to convert. Right? So let's look at this example of a sinusoid. So the blue lines here, this is taken from some NI white paper. They do a lot of instrumentation. So the blue line is the 3-bit resolution of a sine wave. And the purple line is the 60-bit resolution, which is much smoother. How do you think a 1-bit ADC will represent this sinusoid?
two blocks,
Like a
on and off.
square wave, depending on where the threshold is, right? So, what are the costs of increasing the number of bits? So let's see how a very common implementation of a ADC, right? So this is the method is called the successive approximation ADC. So successive means it's iterative. So it does it multiple times. So just from here, you can say, if you add more bits, the conversion will take longer to complete, right? So how this works, so you hook up an input voltage in one of the inputs of your comparator, and you send the result of the comparator to this logic circuit. So when the control signals say, hey, start converting, so are you guys familiar with binary search? So you have, let's say you have assorted values, right? You look at the middle, boom. Okay, is this value bigger than what I'm looking for? If it's yes, then you half your search to the bottom, right? And you ask again, is this current value bigger than what I'm looking for? No, you go up until you actually get where your value is. Same principle, right? So basically what happens here, when you start converting, you output the DAC, the middle part, the middle voltage, and see, and then that DAC will output that voltage to the comparator. The comparator will tell you, hey, you're too high or you're too low. And then after that's done, you go back to logic control logic. If it's too high, okay, that bit is 0. Now go to the next spot of the bit and output that voltage. And so on until you get the actual voltage. Let's do an example. Let's look at that 2-bit ADC module. So you have 0 to 3 volts and 4 intervals. Let's say the actual voltage is 1.85 volts, right? So now you want to know which interval does this value fall into. So first you want to output the middle value to the DAC, which is 1, 0, right? So when you output that value, the DAC will output 1.5 volts. And then you ask, is 1.5 less than your source voltage? If it's yes, then the most significant bit must be 1, just like modulo, right? And then you go to the next part, the next iteration. Okay, the first one stays as 1, and you output 1 to the DAC. That will output 2.25 volts. Now you compare 2.25 volts with your voltage. It's greater, right? That means your actual value is somewhere between here and here. So the final value is 1, 0. Does that make sense? What if you have more bits? How many iterations do you need to do? 1 for each.
1 for each. Yeah.
1 for each bit. Right. Any question?
Is that a DAC?
You need a DAC for this method to work.
Okay.
Right, because you need to actually have a voltage to compare with. So let's do another example. So this one actually falls into the 1-1 interval, right? So same thing, output 1, 0 to the DAC, which is 1.5 volts, obviously less. That means the most significant bit of your result will be 1. And then the next step, 1, 1, 2.25 volts is still less, right? That means the least significant bit is also 1. So boom, now you've found out that your value is in that interval. Do you actually know that it's 2.6 volts? Who said yes? Or what no?
You would have to. This wouldn't work unless you already know.
No, do you know exactly that it's 2.6 volts?
Yes. This
How?
wouldn't work. I mean, you're just trying to find its digital value, but you know you're looking for the 2.6 volts.
Well, when you're the programmer, you read the register value with 1, 1. Do you know it's 2.6 volts?
No,
No, right? You only know it must be between 2.25 volts and 3 volts. So this is something you have to consider when you actually go out there and try to sample analog values. What precision do you need? If it's 10 bits, good. Because 10-bit microcontrollers, well, 10-bit ADCs are cheap. If you need more, and you have to write another proposal to your boss, yeah, I need more expensive part. Any question? One more example. So, point 2, right? The first one is always the same. You output the middle value, 1.5 volts, greater than. I mean, that must be 0. So you go lower range, and then you stick the 0 here. Output 1 for the next bit. It's still more than your actual value. So 0. Is it win?
No, they're just closing the door. You close it real hard.
They messed up, it was the wind though.
Whoa.
That's a heavy storm.
I'm stuck in Tulsa then. So 0, 0, so 0, 0, which tells you that the value is somewhere between 0 and 0.75 volts. That's it. Any question?
Why is ABC in 10 volt in 10 bits instead of like 8-bit?
Why?
Yes.
You know what? I have no idea why.
It's 1,000 divisions is a pretty, you can estimate, you know,
But why? Why specifically 10 bits?
well, it's 1,024 counts, so you can just off the top of your head without pulling out a calculator know that if my range of volts is 0 to 10 and I'm set at 5 volts, you're looking for roughly 500 counts. I mean, it's easy, you know, it's easy for us to do in our heads. If it was 8 bits, what's half of an 8-bit number?
Google, help us. I don't know. Probably that's the sweet spot for like the price to performance ratio. Maybe it's good enough for many people, but not that expensive enough to produce, I guess, even. Because it's pretty common to have 10 bits. Because when you go higher, it's actually the price goes more
Most ones that we
expensive.
looked at were all 10 bits. I was curious.
How come we lost 2 bits in ours? I mean, why are we?
Chopping off the bottom of the bits?
Yeah.
That's
There
your
was-
call.
There was we're not using a parity bit, right?
Right.
So why are we losing another one?
Well, are you talking about the ADC or the UART?
Yeah.
That was just meant that on the UART communication.
Because the UART is 8 bits.
Oh.
It's easier to just transfer it over and chop off the bottom 2 bits.
I see.
So now we've been talking about actually getting the value of an input. Do you think there's other consideration when you try to sample a signal? Is it just the hard voltage value, that's all you need? Is there anything else you may want to consider? Charlie?
You repeat the question. I'm researching to the ABC.
We've been talking about getting the voltage value, right, into a register, like interval, depending on your precision. Is that the only consideration? Is there anything else from the signal you're sampling that you may want to consider?
Times a second, you say?
Time. Why? Why is time important?
Because you need to know when to sample.
Resolution.
When to sample? Why? What's about the signal that you need to know when to sample?
If it's changing, the signal's changing.
Yes. What kind of signals change? Like if it's just like temperature, maybe you just want to sample each point, right? Like you want to sample 5 seconds. That's arbitrary, right? Depending on your application. What kind of signals you actually have to sample at a certain rate?
Music.
Audio, right? If you have taken networks or taking networks, what is the minimum sampling rate for an audio signal for you not to lose fidelity? 8 what? No, sampling rate.
be like, or not to lose any fidelity, it'd be like, I don't know, 190 kilohertz or
That's
something.
overkill.
Can I cheat?
40,
60?
40,
48,
48 kilohertz. Why?
48, because at 44.1 is which is what most like music is sampled at.
No,
Yes,
no. But the reason is why music is sampled at 44 kilohertz.
44.1.
Have you taken networks,
No, but I know this.
Jason? Why 44 kilohertz?
The human ear can't perceive a change faster than.
So what's the highest frequency
4,000?
our ear can hear?
20 kilohertz.
20-ish kilohertz.
Yeah.
Right. When you want to try to sample a signal, you need to at least double the frequency to not lose information. That's why audio is being sampled at 44 kilohertz.
So these audiophile guys with their 200 kilohertz DACs are just
I don't know what
kissing
they're
their
trying
money
to
away,
produce.
right?
Well, because apparently at 44.1 there's still some
Aliasing.
there's some distortion up in the higher, like it from a 16 kilohertz and up. So the jump to 48 is supposed to take that out, but the problem is that most people don't hear that difference anyway. But
Exactly.
mathematically it's there. But
So they're being
there's
honest.
they market stuff at like 192 kilohertz and stuff, but you don't hear the difference because you can't even hear it past 48. So
Exactly.
it's marketing.
Be careful with marketing. So yeah, right. So some input signals you do need to actually sample the time, right? So that means you need to actually be able to sample the analog signal in a regular manner.
Can you repeat what you said a minute ago about you need to sample at twice the rate in
It's
order
called the
to,
Nyquist.
Nyquist thing.
So
it's a universal law of
it's actually people worked it out why that's exactly true. So I'll just save it until you take the networks to see like that makes sense. It's actually pretty interesting. Just look at sinusoid.
what was the name of it so I can look
The
at it?
Nyquist.
Nyquist.
Like for a certain range, everything sounds louder than there's like perceived loudness toward the peak area.
I don't know about that, but so programmatically, we can make the sampling regular if you know how fast you can sample. And it's just about it's just software on how you can actually do the sampling as fast as you want it to be. Make sense? Any question? So sometimes you don't want to just sample the value, you just actually want to sample it at a certain rate, depending on the application. We actually have specialized CPUs called the DSP, digital signal processors, that actually do this kind of thing really, really well. And it actually extracts a lot of things from you. That makes it easier to actually process signals. Things like this, it's a pain in the ass if you try to process audio signal. It's not made for that. Any question? Now the last part, since this is a computing-based system class, how do you think an ADC is exposed to the programmer? The ADC module, how do you think it's exposed to you as the programmer? How have all these different I/O modules exposed itself? Provided the interface to you.
Memory address.
Memory address, which corresponds to certain registers for the ADC. So the official term, I guess, is called a special function register. Basically, on many controllers, many CPU now, they are memory mapped. So if you look at data sheets and you want to see how to control the ADC module, usually it gives you what the special function registers are, the addresses or the aliases. So if you program in C, you don't have to remember their memory addresses. So like UART, usually you have two kinds of special function registers. What are they? Control, to actually set things in motion or configure the module, and no, well, three kinds, but what's the second one? To know the status of the module. Status. And then if you need to actually transfer data or read data, data registers. Right? So you have control, standard data registers. This is very common. No matter what the controllers are, you look at the data sheet, I need to use the USB module. Oh, these are the control registers, these are the status registers, the data registers. On some architectures, the control and status bits are in the same registers, right? So you just have to be careful when you look at the data sheets. For ADC, usually you have the control that sets the sampling rate, which reference voltages you want it to use, and then actually tell it to start sampling. Or if you want to actually have an interrupt that triggers when it's done sampling. So a lot of options and power in your hands, depending on what you want to do. So as the programmer, as long as the resolution and reference voltages are known, then you should be able to understand what the digital value in the register means. Does it make sense to you? So if you set your ADC from 0 to 5 volts, and it's a 4-bit ADC, and you get 1000, you should know what interval that value should be in, right? Yes, Charlie.
Oh,
Oh, yeah, I thought you were.
sorry, I'm listening.
Is this it? Is this all you need to know? To interpret whatever is in the result register of your ADC module. That's it. As long as you can tell it to start sampling a pin, you can just wait for ready flag. When it's done, you read from the register. As long as you know what your range is and you know what your resolution is, you should be able to calculate what that value corresponds to in terms of voltage. That's it. So now if you make a robot or make a device, you can use ADC. If you have a free ADC pin, well, I'm going to make a battery monitor or things like that. So this is why after this class, you should be at least tempted to get some of this development board and see what you can do with controllers, because you can do a lot of things. This is the advantage our major has over something like civil or mechanical. Like civil, oh, I want to build things.
Parking lot, drainage ditch.
Just the overhead of trying to build things from their perspective is, yes, Charlie.
So they were talking to us about the engineering meeting. They said that's a big reason they pay civil engineers more. You can't go build a bridge as a hobby on the weekend, but all these electrical engineers, they have fun doing it and they make hobbies out of
You
it.
should have fun doing it, and you should be,
And the civil engineers don't get the chance.
or Mark as a CS person doesn't have to leave the chair. Just like fire up a terminal. I'm having fun here. Right?
Yeah.
That's what
That's
they
what
do.
your mechanical keyboard driving neighbor nuts.
So get a development board, you can do whatever. Go to Mauser, window shopping, or whatever. And it's fun. Build a robot. It's so easy to make a robot now. Not kidding you. It's like everything is like on an IC now. Or you need to connect to internet to Wi-Fi with the thing. They have the modules as an IC that you can talk through UART. Right? So if you know how to do UART, and you have this module, make sure the voltages are the same, the bot, boom, Wi-Fi. Now whatever product you're building is Wi-Fi enabled. Just for a hobby, just to know like how Wi-Fi works, things like that, right? How do you marshal packets on the TCP/IP, things like that, if you want to go that low. Because they actually have TCP/IP stacked, where you just open a socket on a little itty-bitty chip. So you turn it on, it connects to the router, you can talk to it through telnet. It's ridiculous, right? If you tell this to an engineer from 30 years ago, they'd be like, what? For example, there's so much space in this chip. Like this has 256 kilobytes of flash. Well, don't compare it to your computer. But imagine like an engineer from the 70s. Hey, I have this much data on this chip. Like you can have a help system, like I do, like in this chip. So you don't have to actually open a binder to figure out how things work. Like it used to be the chip, the CPU will just give you code, and you have to decode what the code means. Now you can have this chip tells you what it means. Right, so living in awesome times.
You've seen core memory, right? Actual magnetic core memory.
Yeah, I've been to that computer history museum in Silicon Valley. Very cool. Like this huge memory is like, how much is the storage? Like 56 times 8 bits. What?
It had to be built by hand.
All these wires like coiling around. Then we have flash and SRAM and everything. So we're being spoiled. And it's funny like how all these things end up serving our amusement. And all this computing power. Yes, that's what drives progress. Any question? You just want to make things easier for us. That's engineers, we're slackers, right? I don't want to do it over and over again. Just build this and automate everything.
Automate it, yeah.
That's it, that's ABC. So if I give you a controller and a data sheet, you should be able to start sampling voltages, right?
Yep.
Yeah. So go out there and get a development board. So we talked about ADC, why we have ADC, very useful. Precision and resolution, sampling rate, why we actually care about sampling rate, and the programmer's perspective on how to use it and how this module gets exposed to the programmer and how the programmer can use it properly. Any question?
I saw at Mel's website a paper on. I haven't had time to read it. It was talking about increasing your resolution by oversampling.
Ooh. How do you think that works?
That's
Increasing your resolution by oversampling. I wonder how that works, depending on how the ADC is built, I think.
okay. I need it.
Because I'm not very familiar how they actually build. Because the successive approximation is a really simple system, right?
Okay.
I'm sure they have their own proprietary ways to do things.
So I need to find time to read.
Yeah, like like recording sound cards. Guess what the resolution is? Philip, should know this.
Resolution on sound cards.
Yeah, for recording, like a recording sound card, not just like your typical. 24 bits.
Oh, yeah, 24-bit.
So the chip costs like $15. Just the
But
ADC chip.
it depends what you're using too, though. Like, I have software that can do it in 32-bit.
Well, the actual hardware itself is
The
at
actual
24
hardware
bits.
is 24-bit.
So Cirrus makes a lot of sound chips, like the ADC, high precision ADC chips. It costs like $10, $15 just for the ADC. Now we have like this $1 controller that has 10-bit ADC. So you can see the economies, right? Because maybe people just don't use it, I guess. That makes the hardware much simpler. Pretty cool, huh? Trade-offs. That's the keyword in engineering. Figuring out the optimal solution in your specific application or problem. That's all. And you spend 3 years just studying all these different things, just to be able to make that judgment. Any more questions? So next time I'll have an example of NEC on a PIC microcontroller just to see it in action. I'll have a pot or whatever, potentiometer, to actually provide the voltage and things like that. And then we'll have the review next Monday in the midterm. And then we can talk about probably operating systems after that. That's my area. So, all right, that's all.